Now, another concept that is important to talk about is the idea of half-life. Now, half-life is how long it will take to one of those radioactive or unstable atoms to actually decay over time. And essentially the idea is that it's going to take a very long time for any of those radioactive atoms to actually, well, some take short periods of time, but some take a very, very long time to actually decay to a state that's more stable. And actually what this picture graph is showing you is that carbon-14, for example, okay, will take 5,700 and some years to actually decay about half of what it originally had. So it would take 5,700 and change for half of this carbon-14 to decay. And that's the concept that we call the half-life. Now notice here, you'll start with the radioactive isotope. And then, after one half-life, or 5,730 years, I think, you're going to get half of that becoming a different kind of now more stable element. Now sometimes this daughter element is also unstable and then it goes decay again, like we just saw in the uranium-lead decay series. But sometimes that will be stable. Now, given another half-life, the half of the mother that's left will again decay to become the daughter element, and now you're going to have a little more of the daughter but a little less of the mother. And given another half-life, or another 5,730 years, if you're talking about carbon-14, this will happen again, and now you have a lot of the daughter and not so much of the mother. And that's what's actually showing up in the graph. See, carbon-14 has all these extra neutrons here, which makes it unstable. So that's going to undergo beta minus decay, and you're going to end up with the stable nitrogen-14, which has 7 protons and 7 neutrons over a long period of time. Now, you start at one half-life, before 0 half-lives, with 100% of the original and nothing of the daughter. But after one half-life, you're going to get to the point that half your sample is going to be daughter and half the sample is going to be the original. Give it another half-life, half the original decays again, and now you have 25% of what you used to have, but the daughter is now at 75%. Give it another half-life, and you're about 12% of the original, but the daughter one is going to be around 88%. And so you see how over time you're going to get less and less of the radioactive original and more of the more stable or second generation radioactive isotope. And that's kind of how half-life works. Now, if you know how long the half-life of the element takes place, you can actually use this to figure out how long it's been since it actually passed by. Now, you can use this just thinking about it, or you can do a formula. So, for example, if I tell you about 25% of the atom C14 that was around is around now, you should know, well, one half-life is going to put it to half, two half-lives is going to put it at 25%. So it's been two half-lives. Since each half-life is 5,730 years, that's two half-lives, so it's going to be 11,460 years since that happened. And so you can use that to actually date, and that's kind of how that works. Or you can also use formulas to help you solve half-life problems. And the general formula that you can use is basically this. The mass that you have at a certain time, okay, is going to be basically equal to the mass that you had at the beginning, or the original mass, okay, times 1/2 raised to the power, to the number of half-lives. So M is the final mass, MO is the original mass, and you multiply that by 1/2 raised to the number of half-lives. Now sometimes you can express N as the total time that has gone by divided by the half-life, because that makes sense. Think about it. If I want to figure out how many half-lives have gone by, if I know, for example, that a half-life of a certain element that's unstable is 5,000 years, and I know that 20,000 years have gone by, and I want to try to figure out how many half-lives have gone by, I must divide this number by that number. So the number of half-lives you can find out by dividing the total time that has gone by the time that it takes for each half-life to take place. Alright, so you can express it like that. Now that we know that, let's do a few examples to see if we can figure this out. Now, if you have, say, for example, 50 grams of a substance that is the daughter of a radioactive isotope, and you want to find out how much you had at the beginning of this. So you multiply that by half raised to the power of half-lives. Now, I'm telling you that about 5,000 years have gone by. 5,000 years have gone by. But the half-life of this particular element, or the radioactive element we're talking about, that actually made that daughter element is about 500 years. 500 years. And so you can tell that, therefore, you divide those two together and you figure out, well, this is going to be 10 times bigger, so this is basically x to 1/2 raised to the 10th power. So what you're going to get is 50 equals x divided by 1024. So to solve that, you just multiply both sides by 1024, and you get 50 times 1024. Again, if you need to, you whip out a calculator to figure out that this is actually 51200, I think. So that is the original mass that I had. If the final mass was 50, and about 10 half-lives have gone by according to the numbers that I gave. So you see how you work that one out. Now let's see, looking at this backwards. Let's see, if I had the original mass was 50, and I have now only about 12.5, something like that. How many years have passed if the half-life of this particular thing is 500? 500. Now, when I get problems like this, I look at the exponent as 1 unit, and I worry about that later. Okay, so what I'm going to do here is pretend that this whole exponent here is just n. Alright, it makes my life a little easier. I want to find out the number of half-lives first. Okay, so let's think about that. You solve with algebra. I want to get rid of that, so you're going to be divide both sides by 50, so you're going to get 12.5 divided by 50. Okay, and then you're going to get that equals to 1/2 raised to the power of n. Okay, so now if you simplify that, you figure out that, well, that's about 12.5 times 2. It's going to be about 25. So if you multiply that by 2 again, you're going to get 50. So this is actually like 1/4. So if you simplify that, you figure out it's 1/4. Now, 1/4 equals 1/2 raised to the power of n. Why do I have to multiply this to get that? Well, clearly by 2, right? So in this case, it's going to be the n equals 2. Now that I know what n is, now I go back to the top, and I know t over 500 equals 2. Therefore, t equals 2 times 500, or 1,000 years. And I know exactly how long it has been since that happened. And see how you can actually use this to figure out dating things. And we're going to be using that on the next video. So remember how you do that. Now, another one that you will do sometimes is they will actually give you the original mass, say 50, and then they will give you the number of half-lives, maybe through time, maybe directly. Let's say 4 half-lives have gone by, or let's say, for example, you say 2,000 years have gone by, and a half-life is 500 years. So that's the same thing as saying 4 half-lives have gone by. And then you want to find out the total number of the final mass that you're going to get there. But that's going to be a little easier, because all you're going to do is basically do 50 times 1/2 to the 4th power, and 1/2 to the 4th power is going to be 2, 4, 8, 16. So 50 divided by 16. And that's going to be your amount that you're going to have left at the end of those 4 half-lives. So you see, you can use this formula, depending, just like any algebraic equation, to find out how much you have in the end, if you know how much you had in the beginning and how long it's been. You can also use this formula to find out how much you had in the beginning, if you know where you ended up with and how much time it's gone by and how much each half-life is. Or you can also use this to figure out how many half-lives have gone by. If you need help, watch these again so you make sure how to work those problems out. Alright? Now, that's the concept of half-life, and I hope you understand it.